Good afternoon. I'm Yoon-Sung Kim from Seoul National University. I'm going to talk about Crellvm, which is a verified, credible, or certifying compilation framework for LLVM. Crellvm can be used to improve reliability of major optimizations in LLVM. Let me first talk about reliability problems with production compilers. As you can imagine, production compilers like GCC and LLVM are very stable in most common cases because they are heavily tested. However, they are not so stable in corner cases. For example, random testing tools CSmith and EMI found hundreds of bugs. Indeed, these corner case bugs matter because they sometimes cause real miscompilations in practice, in particular for low-level systems code. So, it is important to improve reliability of compilers even in corner cases. I see. There are various approaches to achieving high reliability of compilers. The most common and basic approach is testing. We test the compiler by testing compiled target programs, which is very effective in finding compiler bugs, but cannot guarantee very high level of reliability. Another approach is compiler verification, which is to directly verify correctness of a compiler using an interactive theorem prover. Although this guarantees complete absence of bugs, it's too expensive to apply to major optimizations of production compilers like LLVM. Another approach is in between is translation validation, which is to check correctness of each translation. Compared to testing, translation validation gives a higher level of reliability because it formally checks correctness of a translation instead of simply testing behavior of the translated target programs. On the other hand, compared to compiler verification, translation validation is less expensive because it just validates a given translation instead of proving that all translations of the compiler are correct. There are several ways of validating translations, among which we think something called credible compilation is a most effective way of improving reliability of production compilers. Specifically, in this approach, the compiler is augmented with proof generation code that generates a correctness proof for each optimization written in a general logic. Then each generated proof is checked by a general proof checker. More interestingly, when validation fails, it derives a logical reason for the failure from the given proof, which is really helpful for tracking the source of bug. Also, by verifying correctness of the proof checker, we can further increase reliability. However, unfortunately, credible compilation had not been properly applied to production compilers like LLVM. So in this work, we developed a verified credible compilation framework for LLVM called Crellvm. For this, we designed a logic specialized for translation validation in LLVM and developed and verified its proof checker in Coq. We applied Crellvm to three major optimizations, namely register promotion, global value numbering, and loop invariant code motion, and also applied it to over 100 people optimizations in the instruction combining path. As a result, we found 4 long-standing miscompilation bugs, which are all confirmed, and 3 of them are currently fixed. Before we proceed, let me show you one of the bugs we found in the register promotion path of LLVM to illustrate how credible compilation may detect bugs that testing misses. Actually, this bug was triggered millions of times in testing because it was triggered in the spec benchmark and had been there for 7 years. Let me now explain what the bug is and why testing missed it, though triggered many times. Look at the following simplified code that is taken from the spec benchmark, where the memtrace path promoted every access to the memory location P into the constant value on def. Let's walk through it step by step to see why this promotion is wrong. First, a memory block is allocated in the source. Then, we read a value from the block, which is undef because it is uninitialized. Here, the undef value in LLVM is a special value representing every possible value. Next, both sides call foo with the same value undef. So far so good. Then, in the source, we store 42 to P and read it again. This time, we read 42. Therefore, the source and the target call foo with different values, namely 42 and undef, which potentially makes the target have more behaviors. This is definitely a bug caused by overlooking the second iteration, which was confirmed and fixed immediately after we reported it. Now, let's see why testing missed this bug. The reason is quite simple. In the spec benchmark, foo happens to ignore the argument R by zeroing out its every bit, and thus they behave the same. Even though they behave the same, Crellvm could detect the bug because it examined the logical reason for the optimization. Now I'm going to talk about more details of the Crellvm framework with examples. This figure shows the overall structure of Crellvm framework. The whole process is divided into two phases, compilation and validation. Since validation takes much longer than normal compilation, we separate them so that validation can be performed later selectively. In the compilation phase, you compile the source program using the original unmodified compiler. In the validation phase, you perform credible compilation as described before. Here, since we only added proof generation code to the original compiler without modifying it, we expect the compiled target program to be equivalent to the original target program produced in the compilation phase. We check this using the LLVM diff tool, which checks alpha equivalence between the two target programs. Furthermore, we verified the correctness of the proof checker in COG. Now, let's see with an example how proof generation and proof checking work based on a new logic we designed for validating optimizations in LLVM. The logic we designed is called ERHL, which stands for Extensible Relational Whole Logic. We will see what extensible means in the next slide. This is a simple example of add associativity optimization included in the instruction combining path. In this code, x is a plus 1, and y is x plus 2. So by associativity, y is a plus 3. So we optimize y to a plus 3. Now let's see how we verify this optimization using ERHL. Since ERHL is a relational whole logic, we first give relational assertions between instructions. Then the proof checker checks the whole triple at each line. Let's look at the most interesting case. We have pre and post assertions, which describe relational properties about the source and target machine states. In the pre-assertion, we have MD equals to the empty set, where MD stands for may-diff set, which is a set of registers that may have different values in the source and target. So MD is empty means that every register has the same value in the source and target. Note that this is a relational property that relates the source and target states. This one states that x equals to a plus 1 holds in the source registers. Note that this is a unary property that talks about only the source state. Now, under this precondition, what we have to really show is that even though we update y with different instructions, y contains the same value in the source and target. In other words, y is not in the may-diff set. Then, thanks to this condition that y is not in the may-diff set, validation succeeds at the next line because foo is invoked with the same value in the source and target. Before we proceed, let me emphasize one important design choice of ERHL, which is that the may-diff set is the only relational property allowed in ERHL, and all other properties should be unary, either about the source state or about the target state, but not about both at the same time. The benefit of this design is that it allows us to do mostly unary reasoning as normally done in unary whole logics, which makes our proof checker a lot simpler. This restriction of relational assertion may seem too restrictive, but actually it is not. I will show you how to express general relational assertions in ERHL in a few slides. Now let's look into details of the most interesting validation at the line 20. Here we have pre and post assertions. First, the proof checker computes a strong post condition from the pre-assertion. This equality is preserved after execution because X and A are not updated by the source instruction. These two equalities are added as a result of executing the instructions in the source and target. Y is added to the made if set because Y is updated with different instructions in the source and target. Okay, this shows how our post condition algorithm computes a strong post condition for this pair of instructions. Now, we need to show that this computed strong post condition implies the given post assertion. Since this is not trivial, we need a proof, which is generated by the proof generation code added to the compiler. First, we are given an ASOC add inference rule, which infers a new property from the existing ones. Specifically, y equals a plus 3 is derived from x equals to a plus 1 and y equals to x plus 2 by associativity of addition. And the existing assertions are simply propagated. Then we are given a reduced made if inference rule, which removes y from the made if set. Specifically, it is derived as follows. First, the inference rule checks that y equals to the same expression in the source and target, namely y equals to a plus 3. And then checks that the register appearing in the expression, namely a, is not in the made if set. After checking these conditions, it removes y from MD. Clearly, this inference rule is sound because y equals to the same expression with the same value in the source and target. Again, the existing assertions are simply propagated. Finally, the given post assertion is trivially implied by a simple inclusion check. So we are done. To sum up, ERHL proofs generated by the proof generation code only consist of assertions and inference rules. Furthermore, we can reduce overhead of writing proof generation code by using a custom automation function that dynamically finds appropriate inference rules, given a pair of pre and post assertions during the proof check. Now, let's talk about extensibility of ERHL. It simply means that we can extend ERHL with any inference rules and custom automation. An interesting point here is that we only need to verify correctness of inference rules, not custom automation or proof generation code. That's because whenever proof generation or automation does something wrong, at worst it only generates incorrect proofs, which should be always detected by the proof checker. Now I will show you the original compiler code and then how we add proof generation code to it. The left-hand side shows the original compiler code for the add ASOC optimization, and the right-hand side shows a translation performed by it. Let's walk through the compiler's code first. It searches for an instruction that adds a constant to a register in the source program. And the instruction at line 20 is matched with register X and constant 2. Next, using the useDef chain, it finds the instruction that defines the register X at line 10 and checks that it is also an addition of a constant to a register. Then the compiler computes addition of the two constants, 1 and 2, which is 3. Finally, the compiler replaces the instruction at line 20 with the new one, adding 3 to A. Now, let's see how we add proof generation code. Initially, we start with the empty assertion at each line, as you see on the right-hand side. Then we write code that generates the assertion x equals to a plus 1 in the source between lines 10 and 20. Note that all necessary data for proof generation are already computed by the original compiler code. So we can easily write proof generation code without extra computation. Next, we write another code that adds the ASOC add inference rule at line 20. Also, the necessary data are already computed by the original compiler code. Finally, we enable the reduced made if automation, which automatically inserts the reduced made if rule at line 20 during the proof check. To sum up, these three are the only extra code added to the compiler for proof generation. Now, let's see how we can encode general relational properties in ERHL using an example from register promotion. Here we assume that the memory location pointed to by P is promoted to a register R. Then we need a relational property stating that the value star P in the source is equivalent to the value R in the target. As I mentioned before, such a relational assertion cannot be directly stated in ERHL. Instead, we can encode it using a ghost register P hat as follows. Star P equals to P hat in the source, and P hat is not in the made if set, so P hat in the source is equal to P hat in the target. And P hat equals to R in the target. Therefore, by transitivity, star P in the source is equal to R in the target. Here, the ghost register P hat is something that exists only logically. In other words, ghost registers are existentially quantified, independent of physical states. Thus, ghost registers can be only introduced by an inference rule, not by any physical instructions. Okay, so far I introduced main ideas behind Crellvm. Now I will talk about the implementation and experimental results. First, the proof checker is written and verified in Coq. For verification, we used the formal semantics of LLVM IR from the Vellum project. We proved a CumSort-like semantics preservation result using CumSort's memory injection technique. We extended the logic with 221 inference rules. Among them, we verified 9 main rules, such as transitivity, reduce medif, and intro ghost. All the other 212 rules are for people optimizations in InstCombine, which we did not verify because we believe that they should be automatically verified using an SMP solver rather than verified manually. This table below shows the number of significant lines of code we wrote for the proof checker. We wrote about 3,000 lines for implementation and about 19,000 lines for verification. Next, proof generation code is written in C++ inside the LLVM compiler 3.7.1. We fully covered register promotion and GVN PRE, that is global value numbering with partial redundancy elimination. But we partially covered loop invariant code motion because some of it used features that we currently do not support, such as general alias analysis. Although we covered 158 people optimizations among over 1,000 ones in the instruction combining path. The table shows the number of significant lines of code for the original compiler code we covered, and that for the proof generation code we wrote. As you see, proof generation code is less than half of the covered compiler code, except for the InstCombine path. For InstCombine, the reason why proof generation code is large is simply because the original code is too short, just a few lines for each path. So while proof generation code has some boilerplate code for each path. In the experiment, we tested the Crellvm framework with large benchmarks, including spec benchmark, LLVM nightly test suites, 5 large open source programs, and random programs generated by C. Smith. So in total, about 7 million lines of C code, which generated 2.3 million tasks of validation. Among them, we detected 464 validation failures, all of which were due to the 4 compiler bugs we found. Also, 25% of them were not supported, mainly due to unformalized language features, such as factor operations. All the rest, 75%, were successfully validated. This table shows execution times. The original compilation phase took 258 seconds in total, which is about 4 minutes. The validation phase took about 123 hours in total, which is about 1,700 times slower than the compilation. However, the validation phase is embarrassingly parallel. So the whole validation was completed within 3 hours using 96 threads. To sum up, we developed Crellvm, which is a verified, credible compilation framework for LLVM. And we applied it to 3 major optimizations and over 100 people optimizations of LLVM. As a result, we discovered 4 long-standing bugs in LLVM, 2 in MemToReg and 2 in GVN. In the paper, you can find more details about Crellvm, such as reasoning about cyclic control flows, reasoning about memory properties, details of MemToReg and GVN validation, and porting to a recent version, LLVM 5.0.1. There are a number of directions of future work, formalizing LLVM IR features in Vellum, or supporting complex analysis, or supporting control flow graph changing optimizations. Thank you for listening.
We have time for a few questions. I can start us off for one. It wasn't clear to me how your framework would support optimizations whose natural correctness arguments would realize loop invariants that held of the code. For instance, strength reduction, where you realize this variable always holds some constant multiple of this other one. You need to know that's true on every loop iteration. Does your framework support checking transformations that take advantage of loop invariants?
Actually, we do something like that we already support that properties, and I think in the MemToReg path I'm sorry. One of the instruction combining paths optimization does that, so we already support this.
How does it look in your proof annotation language that the compiler outputs in so that it can be checked by your Calc verified code? Is there a loop invariant annotation that you can output?
No.
Okay.
But the loop invariant is written in as usually normal assertions in each line. So I think.
And your tool trusts that the assertions are accurate, or it somehow checks that they truly are right?
Our tool checks that every assertion holds.
Okay.
Yeah. I'm not sure I answered your questions.
Yeah, we could continue offline. Thank you.
I have 2 questions. One of them is that you said that your notion of correctness is that equivalence between target and source. We usually get away with less, right? Just that every behavior of the target can be in the source. So why do you switch from refinement into equivalence? That's my first question. My second question has to do with exceptions. You gave the example that you first add 1 and then 2. Suppose you add 1 and then subtract 1, add -1. And you get integer overflow in the first addition. Would you then show that the 2 are equivalent?
For the first question, actually, we use refinement, but for the presentation purpose, we just said it's equivalence. So actually, what we check is refinement between the source and the target. And for the second question, I'm sorry, could you?
Generally, how do you deal with exception? Because on the example that you gave, that you add 1 and then you add 2, on the first addition, you can get an integer overflow.
I see.
And then don't add 2, now add -1. Will you show that the 2 are equivalent? While one does nothing and the other one creates an exception. Source creates an exception.
As far as I know, in LLVM semantics, when integer flow happens, it doesn't produce exception, but it assigns a special value on depth to the register. So I think this how can I say how can I say I'm sorry, could you take this offline?
Sure, we can take it later. Thanks.
Could we have the next speaker come set up during the last question? Thanks.
Yes, you covered, I think, 158 of over 1,000 people optimizations. My question is, did you just run out of time, or is there something that characterizes the ones you did not cover that made them more difficult in your framework?
So your question is why did I cover only 150
Yes.
optimizations? Actually, it is it's because there are thousands of people optimizations, and just it requires very large, very huge human labor. So so actually, while covering those hundreds of optimizations, we thought that this approach is maybe not suited to validating people optimizations.
Okay, thank you.
Yeah.
Okay, let's thank the speaker again.